Hey guys! Alright, today we're going to do section 5 in chapter 6, which is properties of logarithms and natural logarithms. So remember last year in advanced algebra when you talked about exponent rules. So we've got all these different exponent rules. We know that if I divide two exponents, or I divide two bases, then I subtract the exponents. If I multiply two bases, I add the exponents. If I take a power to a power, I multiply the exponents. So some of your basic exponent rules are going to be b to the 0 equals 1. That's your 0 exponent rule. We also know that if I take x to the m times x to the n, that gives me x to the m plus n. So if I'm multiplying those bases, I add the exponents. I also know that if I have x to the m divided by x to the n, okay, if I'm dividing those two bases, I'm going to subtract the exponents. I also know that if I take x to the m to the n, okay, that's when I take a power to a power, and that results in me multiplying those exponents. Okay, so those are just your basic exponent rules here. We've got our 0 exponent rule, we've got our product of exponents, we've got our quotient of exponents, and we've got our power to a power rule here. So basically we have the same rules for logarithms, because remember that exponents and logarithms are just inverses of each other. So we're going to follow the same rules, it's just they're written a little differently. So the first one is your logarithm of 1 rule, which just says that if you have log base b of 1, that's equal to 0. So you'll notice that if you were to rewrite this as an exponent, it would be b to the 0 equals 1, which is just your 0 exponent rule. Okay? Our next rule is the logarithm of product rule. So this is going to be similar to this product rule we have over here. Basically it says if I have log base b of xy, so inside my logarithm I'm multiplying those bases. What I can do is I can split that into separate logarithms that I'm adding. Okay, so that's generally just like the one we had over here, where I multiplied the bases and I split it into an addition with those exponents. Here I'm multiplying the bases inside my logarithm, so if I split it into separate logs, I add them. Okay, we've also got our quotient, logarithm of a quotient rule, which is very similar to this exponent rule. So basically that says that if you have x divided by y inside your logarithm, you can split that up into log base b of x minus log base b of y. So basically, if I've got that quotient inside my logarithm, I can split that into a subtraction between two different logarithms. Okay, I've also got my logarithm of a power rule. So that is like this power to a power rule, where if you take that power to another power, you're multiplying those exponents. So essentially, if I have something like log base b of x to the p, we'll say p is my power, I can move that p down to the front, okay, and it becomes a multiplication problem. So it'll be p times log base b of x. Okay, so essentially what I'm doing is I'm turning this power into a multiplication, whereas over here I did the same thing. I turned this power into a multiplication. Okay, so let's do some problems. Alright, the first problem, we've got natural log of y squared plus natural log of y cubed. So I need to think about how can I simplify this? Well, first of all, I'm going to look through my rules and I'm going to think about which one of these rules can I use. So the first thing I notice is that both of these have powers. So I'm going to start by using my logarithm of a power rule, and I'm just going to move that 2 down and move that 3 down. So I get 2 times the natural log of y plus 3 times the natural log of y. Okay, notice that those are both natural log of y. So basically these are like terms. So I can combine these like terms to get 5 natural log of y. Okay, next problem, we've got natural log of 2y minus natural log of 3y. Okay, so first of all, these are not like terms. I've got natural log of 2y and natural log of 3y. So inside my logarithms, I have different numbers. Therefore, these are not like terms. I can't just combine them. Okay, so what I personally would do first is I would think about changing that into a quotient. So I notice that these are two logarithms that are being subtracted. So I can use that logarithm of a quotient rule and combine them into one logarithm, which would be the natural log of 2y over 3y. Okay, so then when I look at that, I know that 2y over 3y, I can cancel those y's out, and I'll just be left with the natural log of 2/3. And you could go further, but it says to just write it as a single logarithm, so we're just going to leave it like that. Okay, the next one we've got is natural log of 2 to the y plus natural log of 3 to the y. Okay, again, these are not like terms. So the first thing I'm going to do is worry about those powers. I'm going to move those powers down to the front. So I'll have y times the natural log of 2 plus y times the natural log of 3. Then I notice that I've got a y on both of those, so I'm going to pull a y out to the front. So essentially what I'm doing is I'm factoring that y out. I'm taking the y out of both terms. Now looking here, I've got two natural logarithms added to each other. Okay, so remember that when you're adding those logarithms, that means you're using your logarithm of product rule. So essentially you can combine this into a single logarithm where the numbers are being multiplied together. So that would be y times the natural log of 2 times 3. So that's just y times the natural log of 6. All right. Next section, we want to estimate 5 to the 2,000. So what you'll notice is that 5 to the 2,000, if you plug that into your calculator, which I'm sure you're going to try to do, okay, it's going to give you an error. It's going to say overflow error because 5 to the 2,000 is massive. That is a huge, huge number. Your calculator cannot even process it. It's too large. Okay, so what do? Well, we're going to estimate it using scientific notation. So the first thing we're going to do is we're going to say, I have some number that equals 5 to the 2,000. Okay, x equals 5 to the 2,000. Now, if I want to get something smaller than that, I can work with logarithms because I know that logarithms are the inverse of exponents, and you know how fast exponents grow. Well, logarithms, you can get that much smaller in the same amount of time, okay, because they're opposites, they're inverses. All right, so I'm going to take the log of both sides. So I've got log of x equals log of 5 to the 2,000. Okay, then you'll notice over here, this 5 to the 2,000, since that's a logarithm, now I can move that power down to the front. So I'll have log of x equals 2,000 times the log of 5. Now 2,000 times the log of 5, I can plug that into my calculator. And when I plug that into my calculator, I get 1397.94. So that'll be log of x equals 1397.94. All right, so I'm not done yet because I don't have x equals, I have log of x equals. So the base of this natural or this common logarithm is 10. So I can say 10 to the 1397.94 equals x. Now, again, if you try to plug that in your calculator, it's going to give you an overflow error. Okay, so we're not done yet. We haven't finished estimating this. We've just figured out a different way to rewrite this x, which isn't necessarily good enough because that still doesn't really tell me anything. I don't know what this number is going to look like. So what I'm going to do is I'm going to start using my logarithm rules to split this up and make it into something that I'm familiar with. So this 1397.94, I know that that's actually just 10 to the 1397 plus 0.94. So what that means is that I can split this up, since I'm adding my exponents, I can split that up into something where I'm multiplying my bases. So that'll be 10 to the 1397 times 10 to the 0.94. Okay, now this is going to give you a huge number, but this one here is going to give you a reasonable number. So we can plug this one into our calculator, 10 to the 0.94, and when you plug it in, you should get 8.709. Okay, what you should notice is now we have something that's in scientific notation. And that's what we want, because we know about scientific notation, we know what that means. This means that I have a 1,397 digit number that starts with 8709. Okay, so I've got a huge number and it starts with this. Now that's not a very accurate representation, but it's about as accurate as we can get with a number that's this large. All right, last problem on our notes. Okay, we want to be able to rewrite this equation in exponential form. So we've got log base 10 of y equals 3.1 plus 0.03x. So if I want to rewrite this in exponential form, probably the easiest place for me to start would be to start by writing it in exponential form. So 10 to the 3.1 plus 0.03x equals y. So now that I've got it in exponential form, I can start using my logarithm rules and my exponent rules to simplify this down. So here I'm adding my exponents. So that means that I'm going to be multiplying my bases. So I can take this and turn it into 10 to the 3.1 times 10 to the 0.03x equals y. 10 to the 3.1 I can just plug in my calculator. When I do that, I get 1258.93. Now this 10 to the 0.03x, I can't just plug that in because it has a variable in it, but I can get rid of that variable by using my power to a power property, so I can change this into 10 to the 0.03 to the x equals y. Now 10 to the 0.03, I can plug that into my calculator, so I'm going to do that now. And my final answer is going to be 1258.93 times 10 to the 0.03 is 1.07 to the x equals y. Okay, so now I've been able to rewrite it in exponential form. I've got my a, b to the x here, and I'm done. Okay, that's everything for the notes.